Hello all. In this project, we performed EMG signal analysis on the zygomatic major muscle. EMG analysis can be performed either intramuscular or surface electromyography. While intramuscular electromyography has high accuracy and less muscle crosstalk, its infeasibility leads us to continue with sEMG. sEMG or surface electromyography is easy to set up and perform, but it is susceptible to sensor noise and muscle crosstalk, which calls for some pre-processing of signal for medical interpretation. Before connecting electrodes for data acquisition, we applied spirit on the skin of interest. We connected the ground electrode to the collarbones and placed the other electrodes in line to each other near the zygomatic major muscle. Now let's see how we acquired the data.
थोड़ा और हंसाओ मत, उसको करने दो। ठीक है, रिलैक्स, स्माइल अगेन, रिलैक्स, स्माइल अगेन, relax, smile again, relax, now smile again and keep it hold as much as you can. Okay, relax, fine. Do one more time this one. Leave it. Okay, done. So this is the portion where he is.
The electromyography performed gathers the action potential of muscles. In data acquisition, the baseline signal corresponds to no muscle activation when the subject was not smiling. Baseline signal serves as a reference point for comparison with the task signal. The task signal we captured gathers variation with different degree of muscle activation, and from these signals we wish to understand the neuromuscular dynamics of facial expression and explore potential applications in healthcare dynamics. The raw signal that we acquired requires some pre-processing before doing time signal and frequency domain analysis. Firstly, we removed the 50 Hz frequency component as there is a possibility of unwanted power line interference contaminating the signal of interest. For this, we used an IIR notch filter. Secondly, we removed all the low and high frequency components using a 4th order Butterworth bandpass filter. These noisy components were added due to unwanted movement of electrodes when placed on the surface of the skin. Lastly, to perform time signal analysis, we did full wave rectification. The raw sEMG signal contains both positive and negative components which cancel each other out when calculating an average.
Now coming to time domain analysis, our objective was to analyze the muscle activation strength of the baseline and the task signal using two key metrics, mean absolute value and the root mean square value, which are MAV and RMS. They provide key insights into the muscle activation strength during different tasks, as in like the higher the value of these both metrics, more is the muscle activation strength. Now let's look at the values for the task signal and the baseline signal. So we see that for the task signal, MAV and the RMS value are higher as compared to the baseline signal, as the task signal involves the smiling of the subject, and the baseline signal is when the subject is not smiling, so there is no muscle activation. Further delving into the analysis of the task signal for various time intervals, we see that for the first 20 seconds the subject was smiling less, so the mean absolute value and the RMS value are relatively lesser. And for the next 20 seconds, the subject was smiling more as compared to the first 20 seconds. So we see the increase in the mean absolute value and the root mean square value. Similarly, for the next 20 seconds, the mean absolute value and the RMS value are similar. And for the last 20 seconds, the subject sustained the smiling, so we get higher MAV and the RMS value, which implies that the muscle activation was sustained for longer duration as compared to the previous cases, and obviously it is greater than the baseline value.
Performing data processing in the form of notch filter and the band pass filter, and obtaining the required signal, and we analyze the signal in time domain and observe the mean absolute value and the root mean square value of the signal. After that, the next obvious step would be to analyze the signal in the frequency domain, which could provide us with a lot of useful information, and perform some analysis and some variations to the signal in the frequency domain. So the first important concept that we used was filtering. So filtering is a very common concept, and it is used to eliminate certain frequencies or to pass certain band of frequencies. So there are a couple of common type of filters, which includes a low pass filter, which can be used to pass a certain band of frequency lower than a particular cutoff. The next common filters include high pass filters, which could be used to pass a band of frequencies higher than a particular cutoff. Similarly, there are two other types of filters, the band pass filter and the band stop filter, which could be used to pass a band of frequencies or to stop a band of frequency respectively. The notch filter, which you observed, which we used in the data processing step, it is a type of band stop filter with a very high cutoff. So here we use another type of filter, which is called the Chebyshev filter. There are two types of Chebyshev filter. Here we use the Chebyshev type 1 filter, which provides a higher roll-off as compared to the other forms of filter that we observe. Here we use a cutoff of 950 Hz, and as could be seen, the signal rolls off at a very fast rate after 950 Hz signal. So filtering can be useful in various digital signal processing tasks and is used in a wide area of applications. The next step which we did was the similar process we followed for the baseline signal as well. Here also we use the same cutoff, but since the baseline signal is limited to a band of frequencies lesser than 950 Hz, we could observe that the signal starts rolling off before reaching the cutoff. The next step which we did was zero padding. So zero padding is another important concept that is used in various industries and any application using signal processing. So the major benefit of zero padding is it improves DFT resolution, and it is helpful in case of removing spectral leakage, which can be caused when we have a bin at a non-integral multiple of the sampling frequency. So what we do in zero padding is basically we add some number of zeros at the end of the signal. What it will do is it will increase the value and the number of bits of the DFT, and which in fact will improve the resolution, because as we know, resolution is inversely proportional to the number of the DFT number which we are using. So here we use a zero padding factor. So what it means is that if the factor is, let's say, alpha, we add L alpha, where L is the initial length of the signal, we add L alpha number of zeros at the end of the signal. So here if we observe, we use a zero padding factor of 10. So we would be, if let's say the length is 1000, then we would be adding 10,000 zeros at the end of the signal. So a padding factor of 10 is is very large as if seen in industrial aspects, but the why we use a factor of 10 is to actually illustrate the concept of zero padding. As could be seen here, the resolution is increased. If you look closely, the signal becomes quite dense as compared to the initial signal, and so that basically illustrates the concept of improving the resolution. A better illustration can be done in the case of baseline signal where the length is very small. Here we could clearly observe the signal becoming dense, or we could say that its resolution increasing. As you could see, there are some white gaps which could be seen here, but those get filled up after zero padding because of the increase in the resolution. Yeah, so the third important concept which we used was windowing. Windowing helps to window out a weighted portion of the signal, and it is basically useful to remove the discontinuities of amplitude at the boundaries, and also to change the amplitude of the signal based on the weights provided. So we have used three types of windows. First is a rectangular window, Hamming window and Hanning window. So rectangular window is a basic rect function which is used to perform the windowing. The benefit of rectangular window is the attenuation it provides it's normally just around 22 decibels, which is the lowest amongst the three windows that we have used. Hamming and Henning window, they provide a greater attenuation, but they provide benefits in terms of the removal of the boundary discontinuities. So as it could be seen from the plot here, if we use a cutoff of 350 Hz, after 350 Hz, most of the small peaks and discontinuities that were occurring before windowing gets removed. And as should be expected, since rectangular window has a lower attenuation, it provides a higher magnitude as compared to the other two windows. So these and the similar thing we have also plotted for the baseline signal. Here also the similar argument could be made, because the attenuation of rectangular window, it is smaller than that of other two. The amplitude which it provides is greater than the other two windows. And here also, if you could see, the discontinuities at the boundaries, they get removed off, and there is quite a smooth transition at there. So these were the major three concepts which we used for our analysis and frequency domain. There are a lot of other concepts as well, but we tried to cover them in the earlier steps, that was during the data processing or during when we were doing the time domain analysis. So yeah, so that's it in the frequency domain, and we would like to end our presentation here with the following conclusion. So first is, any physical signal, if you acquire it by physical means, it is bound to have certain noise, and it
Moving on to the conclusion, any signal that we acquire is bound to have some noise, and therefore we must do some signal enhancement and apply the concept of digital signal processing. From the frequency domain insights, we can capture the important frequency component associated with the Zygomaticus muscle, capturing the dynamic nature of the muscle, contractions and expressions. By recognizing the pattern, we can use it in the medical studies and do some early detections of any anomaly of the patient, which could help us in aiding early diagnosis.